Good morning. We are going to start today with another important module of our course, Vehicle Dynamics. And we are going to study about a straight line motion of our vehicle. That's called longitudinal dynamics, otherwise called a vehicle performance study. Right? So what do you mean by vehicle performance? So that refers to the vehicle, how a vehicle is good at accelerate its vehicle so quickly it has to gain its expected speed, or how good it is in braking in straight line. So if there is a sudden obstacle, then if I apply the brake system in my vehicle should be such that it has to stop and respond to the driver expectation that it stops in the shortest distance without any skidding of the vehicle, or how good it is able to grade the road. So if I have to take my vehicle uphill, or if I have to go to a mall and I have to take my vehicle in a ramp, then I should have comfortably able to take my vehicle uphill at a grade. So if your vehicle is good at to accelerate or brake or to negotiate the given grade, then you would say your vehicle is good performing vehicle. So our particular study now for another 4 lecture also is going to focus on this longitudinal dynamics aspect of our vehicle. So we are going to take again a passenger car for that study. So what are those important things in this particular module of longitudinal dynamics that we are going to study? So we are going to look at how much can be the maximum tractive effort that the vehicle can develop. So vehicle can be particularly a passenger car can be a front wheel driven vehicle or rear wheel driven vehicle or all the wheels driven vehicle. So if your vehicle has to develop a maximum tractive effort in order to meet this requirement of vehicle performance, then what is the maximum traction that can be developed as a function of vehicle parameter is what is in first hand that we are going to look at it. And then we are going to look at today's vehicles are most of them are IC engine powered vehicle. But today, tomorrow's field, tomorrow scenario is going to be more of e-mobility. Upcoming vehicles, more talk on today's automotive industry is e-mobility. So we are going to have almost another decade or two. Also, complete replenishment of our existing vehicle powered by IC engine and powered by electric motors. So if that is so, then how is that the challenge of your vehicle dynamics going to be there, right? So that is all you have to study. So IC engine based vehicle may require now you see that the design aspects of your vehicle subsystem, you see the transmission system is very important. If you do not have a transmission system in your vehicle, you may not be able to use your IC engine to tap the required tractive effort to be developed at the tire road interaction, right? You may not be able to provide the required driving torque to the drive wheels from the IC engine for the different operating condition or that you want to drive your vehicle. Whereas that cannot be the case in your e-vehicle. You can have hub motors on the wheels. You may not be requiring a complex transmission system and so on. There are many things that you have to look at. Whatever that we do now, vehicle dynamic study, with the perspective of electric vehicles. So that's a challenge. That's a people diverging into looking at an architecture of your electric vehicle. The distribution of mass in your vehicle, an IC engine based vehicle may be different than that of electric vehicle. So how your dynamics of your vehicle is going to be influencing all are the talk or the focus today engineers are looking at and learning, exploring. So now started in this particular lecture, on acceleration of your vehicle. On the other side, you see is braking. So the braking vehicle should stop at the shortest distance in a straight line. And you see there are advanced control strategies called the anti-lock brake system do play a role in having good braking force distribution among the wheels. so that your vehicle can brake safely. So we are going to study an anti-lock brake system and its functional aspects, and we are going to look at the dynamics of tire wheel assembly and see how the braking force distribution has to be distributed, and it is going to be depending upon not only the load of the vehicle, also the texture of the road. The surface nature also is very important. So this is all something that we are going to do focus and study in our longitudinal dynamics. So this is what in short that we are going to do in another 4 lectures also as we complete our longitudinal dynamics. So what is my today's objective? I'm going to just look at a vehicle and see that what is the load distribution of the vehicle which is stationary. When I start my vehicle and power my vehicle to accelerate vehicle, what would be the change in my loads on the wheels. And then I'm going to derive an expression of maximum tractive effort that can be developed at the tire road interaction in order to translate my vehicle in a straight path. So that's what essentially in today's class that we are going to look at. In that study, we are going to look at what are the external resistance forces that are acting on a vehicle, and that has to be overcome by the developed tractive effort at the tire road interaction. And this developed tractive effort has got 2 limitations. One is that it is that how much is the tire road ground force can be supported by the ground nature. So the ground adhesion coefficient, something called coefficient of adhesion, that's called, it depends. So based on that and the vehicle load, you would have the limiting value of your tractive effort. Or on the other hand, how much can the power plant of your vehicle can provide the tractive force. So the torque that is being provided by transmission to the wheels and the road nature, there are 2 aspects that is going to limit your this tractive force developed. So that we are going to see, and then we will look at some transmission system and so on. That is how we are going to go ahead with our this particular module of longitudinal dynamics. I'm going to share my screen, and then let's look at an important derivation, understanding what are various forces that are acting on a vehicle, and then how do we going to get our maximum traction in terms of vehicle parameters at the end of the lecture, and also comprehend what are the important assumptions that we make to derive them, right? So that's what is today's particular class we are going to learn. So let me share my screen. Hope all of you are able to see the screen. And this is lecture number 36, and today's date is 22/11/2021. And we're going to start with the next module, and that's called longitudinal dynamics. Longitudinal dynamics, or otherwise called vehicle performance. So when I say this vehicle performance, as I said, it depends upon how good the vehicle can accelerate or can decelerate or braking. So what do you mean by deceleration? If you are reducing the acceleration, that's called deceleration. So if you are accelerating your vehicle and suddenly you are taking a foot from the pedal, what is happening? The vehicle is decelerating. The speed of the vehicle start reducing. That's deceleration. Braking is that you apply brake pressure in your wheels and then generate the braking force, and that is going to assist deceleration quickly and then vehicle to stop. So how good your vehicle can decelerate or brake in the event of necessary condition, correct? Necessary situation, or how good it is to negotiate the grade. in a straight line motion. So this is very important. So this accelerate, decelerate or braking or negotiate the grade all are in a straight line motion. So this is a study about 1D motion. Right. So the vehicle translation is all because of the rotation of the wheels, and the rotation of the wheels all because of the drive wheels of your vehicle is given a torque, and the torque is given by means of the transmission, which takes the torque from the power plant of the system, that can be either IC engine or an electric motor, right? So in our case, we are going to look at IC engine based passenger cars. And what is the today's classes? How much is the maximum tractive force? So maximum tractive effort that can be developed and supported by the road surface. By the road surface. So the word here supported is to be something critically looked at. So how much can be developed and how much can be supported is what is very important here. So how much can be supported is dictated by mu p times w, where this mu p is what is called coefficient of road adhesion. Coefficient of road adhesion. You should not misunderstand this mu with the coefficient of friction. So of course the road surface and the tire road interact, and that is having some roughness, and the rough surface is characterized by coefficient of static friction, is all something that we have learned in our fundamental engineering mechanics course. But when it comes to the interaction of your pneumatic tire with your road surface, what is that coefficient that we talk is coefficient of road adhesion. So this is what something you have to see. So that coefficient of road adhesion is defining the road texture or the road roughness and its interaction with the tire. When the tire is not skidding, when the tire is not sliding, the tire is rolling without sliding, then you call that as mu p. If the tire is, instead of rolling, the tire is translating, sliding, the contact patch with the road is sliding, then I don't call that as a coefficient of road adhesion, then I will call that as a coefficient of static friction, right, which you have studied. So when I say that, immediately what is that comes in your mind is that what is that we are defining once again. Let's look at the tractive effort, whatever that we are going to have effects, and that's going to be function of an important parameter called I. What is this? Is called longitudinal slip. Longitudinal slip. So you should immediately connect this longitudinal slip to that what you have learned in your lateral dynamics, the slip angle. So the lateral force developed in case of cornering is depends upon the slip angle. So that's what we have looked at. It is given by C alpha times alpha, where C alpha is what we call it as cornering stiffness. But now this Fi alpha is not going to be there in the tire road interaction, as it is 1D motion, and we are going to look at the Fx, and that Fx is going to be function of this. So I can also define this Fx as Ci into I, where this Ci is what is called longitudinal slip stiffness. We are going to love this. Longitudinal slip stiffness. So we look at this all again in detail, definition of I, right? If I ask you how do you define alpha, you know that it is an angle by the wheel travel direction to that of wheel plane. When I view from the top view, you would say that is slip angle. Similarly, you can define this slip, longitudinal slip, as it is going to be the ratio of the longitudinal speed difference divided by the tire when it is rolling with the free condition. So we will define that slip, longitudinal slip later on. At the moment, you don't worry. For today's class, I will just explain you that according to the requirement, the situation. At the moment, you just see that there is something called longitudinal slip, and that is what is here creating the necessary tractive force. If you look at the mechanism of development of force. So if you see that variation would be linear for some time and then it would be non-linear and it will attain the peak. So it will be linear till say this point, and that is what is your critical slip value. And you would have here the force generated would be generally approximately half the MEP times W, and then it goes to the peak and then it falls suddenly. So this peak corresponding to that is what is given by MEP times W, where this MEP is what is that we define coefficient of road adhesion. And this value is corresponding to your maximum value of slip. And the slip has to happen. That means that there should be a part of the contact patch to slide and then the part of the contact patch to adhere. Then it is not complete sliding. So that means that's what is called the phenomena of slip. That means if I drive my vehicle, my wheel only if I observe, then what is that an equivalent translatory motion of my wheel center for one revolution when I apply a driving torque. And if I don't apply the driving torque and if I look at free rolling wheel, and what is that for one revolution, the translatory distance, if I observe, the second case would be more than that of the first case. So the difference in that distance divided by what is that your rolling condition, your rolling condition. So let me just define you that so that you would have clearly to go ahead this I to define. I define that I as 1 minus or V minus, let's take this is V minus R omega by R omega. So what is this that to understand? R is what is free rolling radius, free rolling radius, and omega is what is angular velocity of the wheel. And V is what is wheel center translational velocity, wheel center velocity, forward velocity, right? Or you can say that's vehicle velocity also. So there will be difference in this. So what is this V? So when you are applying, your torque, so the driving torque when you apply, you see this R times omega would be greater than V when driving torque is applied at the driving wheel. R times omega is what is R is free rolling tire. So when driving torque is not applied, for example, my vehicle is a rear wheel drive vehicle, and my front wheels are not supplied by the torque. So R times omega of my free rolling condition. So the operating condition of your tire, when you can say tire when it is freely rolling, tire when it is applied with the driving torque, when it is applied with the braking torque, like three different scenarios you will look at it. So if you look at one tire rolling without any torque is what is R omega, and with the torque is what is manifesting this V, then you see this R omega is greater than V. That means what? the translation and distance for one revolution, if I look at, that would be smaller than, that of, that would be, right, 1 minute. That I have written in another way, right? So this is for generation. So I love to write this in another way. So are you able to listen so far whatever that I have taught? Was that my board was visible to you all? Any response?
Yes, sir.
Yeah, so far no worry, right? Suddenly some data issue that I have to switch over to the mobile. Yeah. Let's continue with that. So my screen is visible to all of you, right? And so far, whatever that I have written on the board, you are able to go through. So let's continue from the point of defining longitudinal slip. That is defined as this relative speed. That is the tire when it is rolling freely, whatever is my equivalent translation of my translative velocity of my wheel center is r omega minus when driving torque is applied is V. Why is it so? Because when there is a driving torque applied, there would be a compression of your tire tread as it enters the contact patch. So the circumference would be smaller than that of what would be the free rolling tire. That's why this slip phenomena that occurs. We'll see that in detail again later. So this by this would define and multiply by 100 is what is your longitudinal slip, right? Okay, so now if you look at once this force is developed because of MEP times W that is acting on a vehicle on that's a net load of the vehicle, and you get your I value developed goes to this maximum value, but once it reaches the maximum value, what will happen? The slip cannot happen continuously. So as the slip increases, that sliding of your tire at the front of the contact patch would be progressively moving towards the trailing end of the tire. So as it is going to the trailing end and it is just about to finish its travel of sliding or the zone, and you get this point. So this is where you get the maximum tractive effort possible. So that's where your control system, traction control system all do work, so that it would take care that your I value with the tire rod interaction will not go beyond this, and it would ensure the maximum possible traction that can be supported at the tire rod interaction. So that can be supported, that's what I'm saying. So something that I values increases further here, what would happen? That would suddenly, no time would fall to a value corresponding to MES times W. So at that time, you see that tire instead of slipping, it will be sliding on the road surface. So that's where this is sliding. At that time, there is no rolling action of your tire wheel assembly, right? So we don't operate, or the tire will not go to this state unless and until you apply brake. Similar way, you can also look at instead of tractive force as a braking force. You'll see that in later. Correct. Today's class, no, I'm not going to further go into this tire and the phenomena of force generation in the tire. We'll look at that separately. Just understand that in an analogous way, we look at the cornering force. We can look at our longitudinal force by this, wherein I'm defining this important stiffness called the longitudinal slip stiffness of the tire. Right? Okay. So this value is limited by MEP times W now. That's one. Another thing is that how much is being provided by the engine torque. So that torque by your efficiency and force, right? So you have an expression for the driving torque applied, and from that the corresponding tractive force would be obtained. How? You divide that by your tire radius, and then divide by mechanical efficiency of transmission and so on, and then account some mass loading effect, and you would have some tractive force. So smaller of these two conditions, one is how much can be supported, another one is how much can be provided by the engine. Smaller of that would decide the performance potential of your vehicle, and that's what we are saying. The performance potential are 1, 2, 3. These are the three aspects. Right. So let's now draw the free body diagram of our vehicle, and then look at what are the various forces acting on the vehicle to derive the maximum tractive effort. So let me look at a passenger car, and that's nicely on the horizontal surface parked. Right. So I would have now, if this is part, its free body diagram is what the weight of this vehicle would be acting somewhere here. Its total weight. And then I would have support reactions. So this is WF and WR. WF and WR. This is a parked vehicle. And you know the geometry of this vehicle is described in this view as wheelbase, and that wheelbase is again divided by this ratio L1, L2. So where L1 is the distance of axle from the CG location along the longitudinal direction, L2 is the distance of rear axle from the centroidal location. So the centroid location will not change, and it will be same here when it is a stationary vehicle. But now what is our longitudinal dynamics? This vehicle has to accelerate, and if required, it has to negotiate the grade. So I'm going to look at now the same vehicle on a slope. Pardon, I have not drawn the same. Just want to. The same vehicle. Consider the same vehicle, and its weight is here now, and that would be now divided into two components. That would be now divided into two components. Let me have one component along this, another component along this, the total weight, right? So this I call it as RG, grade resistance, and that would be W sine theta S. What is theta S now? Is the slope angle. So this is theta S, is the slope of this road surface, and I have now the same, this distance is L, and this distance is L1 and L2. So we also have looked at, instead of L1, L2 in lateral dynamics, we have written A, B. That's for our convenience. So let's now follow in longitudinal dynamics L1 and L2. And this W is what is now resolved into this. So if you look at, I'll have my weight as this, and this is what is now resolved into these two components, right? And of course, I will have now here my normals. This is WF, WR, sorry. WR. This to support this component, which is W cos theta S. This component is supported like this. And this is the load now on the vehicle acting or giving, pushed down on the ground, and that's supported by this WF and WR. So the value of WF and WR here can be simply obtained from your drawing free body diagram, right? So this is parallel force system. So if I take moment about, so let's call this contact surface is A, and this contact surface or the contact patch with the road is point B. Then taking moment about B, I would get what is WF. And that would be equal to W L2 by L, and WR I'll get W L1 by L. So this, how do I get? By simply taking moment about point B, considering convention counterclockwise moment positive, I would be able to get this, and taking moment about point A, I'd be able to get this. So this is what is static load distribution called. Static load distribution. So this is from your engineering mechanics, just like you take moment and you are doing it. And this is again, you are going to look at now the diagram, which is dynamic equilibrium diagram. The dynamic equilibrium of the system. So that means what? It is accelerating up the hill. So there is an acceleration of the vehicle A. So it is increasing in its velocity as it goes over this slope. So if I have this acceleration here, I would have my free body diagram, the D'Alembert force that would act in this direction, and that is W A by G. So mass times acceleration is what is now D'Alembert's force. If I apply Newton's law, I will not put this diagram here, and instead I would have rest of that, and that's what is equal to a car with this only force WA by G at the CG location in a forward direction, right? That's what you know that, and this is your dynamic equilibrium, and I have this D'Alembert's force now acting at CG location in this direction because of this acceleration. And in addition to that, there are various resistance forces that are acting. So one important resistance force is aerodynamic resistance force. So that's with the subscript R. So resistance, so I put it in R letter, and aerodynamic resistance, and that would act at that height, say approximately HF, and this would be the line of action of this resistance would be at the CG location of the projected area of your vehicle. So projected area of the vehicle means you look at your vehicle from the rear and then project it on a wall at orthographic projection, and you get a rectangle accommodating your on the width of the vehicle and the height of the vehicle, and then you would get the CG location. That's where this aerodynamic force would act. And you also have in every vehicle a towing purpose. You have connection. So I have here some resistance required if I have to tow something. So that's what is called a drawbar resistance. And then apart from that, I have an important resistances. One important resistance in the front of the axle wheels, that's called rolling resistance. We'll look at what is rolling resistance in detail again later on. RRF, rolling resistance in front, and rolling resistance in the rear, RRR. So now, in addition to that, now I can have my another important force that is very much important for our today's class. That is the tractive force. So because of my drive wheels. So if I consider my drive wheels are all four wheels drive vehicle, if I consider, I will have my tractive force that's acting here as well as here. So this green color is what is coming because of all wheels driven vehicle is this. If I consider four-wheel drive, and this is my FF, tractive force in the front and tractive force in the rear, FR. So this is all the free body diagram of my vehicle which is accelerating up the hill. So if I do that, then immediately I can be able to generate my governing equation. What is my governing equation here? All the forces in my forward direction plus an inertia vector or D'Alembert's force is what is equal to 0 is what is my governing equation. Right? So let's call this is my direction X and this is Z direction. And if I have my ISO coordinate system at CG location, you would have to have your right hand coordinate system fixed like this. So your index would be forward direction, this would be vertical direction, and this would be from right to left would be positive Y direction. So if I have this and I have now can be written my equation. So putting into this, I would have what now? Both tractive force FF plus FR, and you see the rest of the forces, all horizontal forces in opposite direction. So that's going to be RRF, RR, rolling resistance in the rear axle. So these are the forces at the tie rod interaction. And then I have an important force, the aerodynamic force, and I have an important force RD. So this is at a height H drawbar bull, so HD, and this height from the ground is CG location H, small h, right? So RD, and I have of course this RG and minus the D'Alembert's force, G all equal to 0. So this is my equation number 1. So from this equation, I can write my total tractive force is these two. So that's going to be F, the total tractive force, F equals. On the other side, I'll have all the resistance. So this resistance is rolling resistance. So I'll just simply take it on the other side. That is RR. And then I have this aerodynamic resistance RA. And I have this RD. And then I have this RG. There are 4 resistance plus this vector WA by G. So there are 5 forces here, that's equal to 2. So this is my total tractive force, that is now. From this simple equilibrium equation in the longitudinal direction, when I put, I get this equation. So here, what are the forces that are developed at the tie rod interaction is what is making this to go forward. So the net force, if I have to look at, that would be this force minus this rolling resistance, these two, right? Sorry, not that two, these two. Rolling resistance. So I'll take this rolling resistance on the other side, and then remaining all on this side, let me keep. So that's going to be first aerodynamic force. Then I have my drawbar pull. Then the force that is grade resistance, that would be W sine theta S plus WA by G. So let's call these are all the resistance, and that to overcome and to have a motion, you have on this side your net tractive force. So let's call this equation number 3, right? So now I'm just going to find out now here. So I know when it is not accelerated, I have my load distribution is given by these two expressions. But if I have acceleration, then what will happen? If I accelerate, what will happen? The load from the front to the rear would be transferred. So I will have more load on the rear axle than that of the front axle. And the other way, if I suddenly apply brake, what will happen? The load from the rear would be transferred to the front. That's what when we apply brake, we go forward. When you suddenly accelerate our vehicle, we feel to go backward. So that is that way you can remember that the load. So how much is that increment in this, and how much is the decrement in this, is what now we have to look at it. And for that, I need to find out these two normal loads from this free body diagram. So that can be done simply taking moment at point B, that is contact patch at the rear, and I can find WF, and then take moment about point A, I would be able to get this. So here I had only load and no other forces because vehicle stationary, but here I have many forces. Now I have to do this carefully, and then I get my dynamic load transfer components. Right. So let me just write down this equation. You can look at the free body diagram once again and carefully do it yourself once. And considering counterclockwise moments positive, I'm taking moment about point B on the free body diagram on my right, whatever that I've just now shown. That's going to be now WF is in front axle into wheelbase distance L minus next moment is what is by weight W sine theta S into L2 plus I have aerodynamic resistance, that's RA into HA. So why this is plus here? Because it's counterclockwise moment at this. So see, this is RA and I'm taking moment about this. So this would create a moment about this point is counterclockwise moment. That's why plus RA into HF. HA. This is HA. So similarly RD into HD. And I'll have all the other moments by these forces. So I would have now plus RD into HD plus. So this component only was clockwise. So look at now WA by G is in this direction again, same. So that is WA by G, and this is at the height H. So this are the components 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and anything is left. So 1, 2, 3, 4, 5, 6 components. So 1, 2, 3, 4, 5. One more. What is left? One more. Gradability. Gradability. That's this. So this is W cos. Sorry, I'm sorry. This is W cos the weight component into L2, and here I'll have gradability also is positive. That's going to be W sine theta S into S. So the grade resistance force into H is all equal to 0. So from this I would be able to get my expression of WF. So now the for WF is going to be bring this all on the other side. So this is going to be WL2, and considering theta S is very small angle. So cos theta S is going to be 1 and sin theta S is 1. Theta S. So what will happen? So this term is going to be WL2 by WL2 by L, because I take this L down, and this all, see, this all I'm taking on the other side and doing it. So next step from this equation number 4, I'll get now equation number 5 is this minus, I take H by L out, and inside I'll have RA. So this minus sign because this goes on that side. So RA plus RD plus WA by G plus W sine theta S. So you would immediately get, so this all are nothing but F minus RR. That's what is our equation number 3. See, look at the same term, I have it here. So this, let's call this equation 5. And similarly now, see WL2 by L, from there I am subtracting this factor. So this all summation of this force multiplied by this factor H by L. Right? So that much part is what is removed, and this part is what is now responsible for your dynamic load transfer. And this is the term, first term referred to static load, and this is the dynamic load transfer part. So that you have an instant of acceleration, WF is this. So similarly, now taking moment at point A, I would be able to have another 5 minutes. I will complete this lecture, and WR I will have, and that would be equal to, I'll leave it to you to write this equation similar to 4 and then reduce to WR. That equation is W L1 by L. See, now look at here, it's L1, and instead of minus sign I'll have plus sign H by L, and I'll have inside the same term RA plus RD plus WA by G plus W sine theta S, and that would be equation number, I'll call this equation 7. Equation 6 is, what is this equation? So I leave it to you to fill this, and then you have this. So now from 2, equation 2, my equation 5 would become WF is going to be WL2 by L minus H by L into F minus RR. Let's call this is equation number 8. And WR is going to be WL1 by L plus H by L F minus RR. That's equation number 9. Right? So now we look at, I have replaced this all resistances by only this, the forces at the tire contact patch. These all of course acting on the vehicle body, but you look at now, I have my load at the front and rear axle is given by this expression, right? I know this, what is there in this bracket is what is equal to these all resistances. So if you look at these resistances, this is very interesting. They are function of speed. So if I look at all the resistances that are there in a vehicle, and because of that resistance to overcome, what is the power requirement? That's what road load power we call, road load power. Why? Because you have force and velocity is what is power. So if I take this and I would see that the mechanical load power would be gradually going like that. Whereas if you look at an aerodynamic resistance, initially it is appearing smaller, might be smaller than this, but as the speed increases, this would go with a higher rate. That's why, because of the rolling aerodynamic resistance. So that's been given by aerodynamic resistance itself is a topic and subject for vehicle longitudinal dynamics. And we just look at that force can be given by this expression of rho CD A into V square. So where this rho is mass density of fluid, air density. In this case, because the vehicle goes and the air impinge on the vehicle and it goes against, and CD is what is drag coefficient, and what is A here is projected area, and what is this V here is vehicle speed. So what is the power requirement to overcome your aerodynamic resistance? Is RA times V. So that's going to be half rho CD A VQ. So look at now. If I have my vehicle driven, say here it is 50 kilometers per hour and here it is 100 kilometers per hour. So when I double the speed, the requirement of road load power to overcome this resistance RA, and these are other resistances, say rolling resistance and drawbar resistance, other resistances that are there, mechanical resistances. So this aerodynamic resistance is going to be increased. So if velocity is doubled, then power requirement is eightfold. That's what we should see, that vehicle aerodynamic design aspects are very important. That's where the product development as the vehicle, if you look at the vehicle body profile, is very important. You should have smooth streamlining of your resistance here that comes on your vehicle to get out of the vehicle as you are accelerating up. So there are wind tunnel tests and either on a prototype vehicle or a real type vehicle to be carried out to estimate this resistance and hence this value of CD. So it's around 0.43 for a passenger car, right? So at higher speeds, the resistance are more. So this is all to be overcome, and that's what is we call it as road load power. So the force F minus RR, this RR is the local material phenomena of your tire with the interaction with the road surface. So the net force that is developed should take care of these all resistances to make your vehicle to translate. So that's what you look at here, the importance of aerodynamic resistance that we just looked at. And we have just got now these equations for the normal loads of the vehicle front and rear axle. So now here, my next objective this derivation is to find out what is the maximum tractive force in terms of vehicle parameters. So that is the point in the next class we will look at as a starting point, and we will just going to rework on this equation 8 and 9 and then show the expression for maximum tractive force to begin the next lecture, and then we'll go ahead with that, right? So with that note, I'll stop today's class, and if you have any doubts you can ask, otherwise I'll end the lecture.